So there's a few reasons why linear differential equations are nice to look at. And specifically, again, let's take it back to the very first section of this class when we talked about differential equations. And we really are pushing this class as differential equations are useful because of mathematical modeling real world situations with equations, and derivatives are very helpful when you're doing that. And again, we have millions of examples of that. We'll see more later on in the quarter. We got some big examples, application focused sections coming up in the next couple chapters. So when we're modeling linear equations are good models. All right. Now I'm going to say they're great for modeling. It's maybe a little gung-ho, maybe a bit of an exaggeration, because of course linear equations are simple models, right? But a lot of times simple models are great. Simple models means it's usually pretty easy to solve, and we can see what's going on pretty easily. Of course, we oftentimes sacrifice some realism, we sacrifice some accuracy. But, it's a trade-off, right? How much accuracy do we want, and how much do we want to be able to work with the model itself? So, they're not always the best for modeling. Usually they're good starts, honestly. And then we can say, all right, this isn't enough. This isn't strong enough. I need something more. And then we can make things more complicated, right? But they're great starting points for mathematical modeling. And then another reason why things are great is that solutions to linear differential equations are all related to each other, okay? And now that may or may not be good things in other aspects of life, but in differential equations, being related, having all the solutions all related is fantastic. And I'm going to show you why with introducing this linearity principle. So we have a linearity principle for homogeneous equations and for non-homogeneous equations. We'll start with this one. So here's your linearity principle. It's really nice. All right, and very powerful. So if we have a solution y sub h of t, if that's a solution to the differential equation, the first order homogeneous ordinary differential equation, I'm just going to write it like this, equals a of t times y. Again, maybe I'll put in parentheses, right? This is homogeneous, this is linear, this is first order. It's an ordinary differential equation, right? This is a very specific type of differential equation, specifically linear. So although there will be versions of this for higher order differential equations as well, it doesn't really have to be first order, but anyway. If we have a solution to a homogeneous differential equation like so, then k times that solution is also a solution. And this works for any real number k. All right, so you find a solution to a homogeneous differential equation, multiply that solution by any constant, you still have a solution to that same ordinary differential equation. All the solutions are related. They're just all constant multiples of each other. So let's see what that looks like. But before we do that, this is a very easy proof. Okay, so let's just go through it real quick. How would we prove this is the case? And this is a great opportunity for anyone going at a higher level of mathematics. If you want to practice your proof writing, this one's fairly straightforward. How do you prove an if-then statement? And specifically, how would we do it for one like this? You could pause the video, take a moment to think about it, but you don't have to. So to prove an if-then statement, we assume the hypothesis and try to show the conclusion is also true. So to do that, we're going to assume that y sub h of t is a solution. What does that mean? That means that you plug it in, it makes it equal. So we want k times y sub h of t to be a solution. To do that, we need to show we want this to equal a of t times that solution. Right? If the derivative of a function is equal to a times that function, it's a solution to the differential equation. So let's look at the left-hand side and see if it equals the right-hand side. So, well, this is a constant. It comes out in front. What's the derivative of y sub h of t? Well, we already know. It satisfies this differential equation, so its derivative is just a times y. Oh, we're done. Right, all we wanted was this. We got it. Well, that's the right-hand side. Okay, easy proof. That was short. Check mark, smiley face. That's really all there is to it. All right. Because of how derivatives work. Now, I have another question for you before we go on to some examples. Is y equals 0 a solution to every first order homogeneous linear differential equation? Think about that. Let me know what you think. I'm not going to give you the answer right now, but think about it. All right, let's look at two examples, and we'll see the linearity principle in action. Then we'll move on to talk about the linearity principle for non-homogeneous differential equations. So we're going to start by looking at this differential equation, dy dt equals cosine of t times y. Again, we can make some observations about this differential equation. It is not autonomous because it depends on t. It is separable, so we should be able to solve it. And in fact, we can solve it. We could find the answer. You know, you could pause the video if you wanted more practice solving separable differential equations, practice with your integrals. But you're going to find that, you know, our solution is k e to the sine t. And whether you deal with a constant from integrating and you have the constant of integration, you can call it k, you can call it c. The book really starts just calling it k all the time, I think because of the notation of the linearity principle. But it's just like the c from before, and you can see that the general solution, right, is just one solution times any constant k. And we'll see that in the, I think the next video with slope fields. No, we'll do it. We'll look at the slope field right now. Right, what does this slope field look like? We already have it plotted. And you can see that any solution I plot will look like a different solution multiplied by a constant. And again, y equals 0 is an equilibrium solution. Right, you can see these are all just vertical stretches of one another, those solutions. Okay? And we're going to look at another example. We'll talk more about the qualitative implications of this as well. And in the next video, again, linear homogeneous differential equation. The solutions are all going to be scalar multiples of each other. So in the next one, I want you to actually close your eyes. No spoilers, no cheating. Don't look. I'm going to type in an equation, and I want you to decide whether it's linear and homogeneous or not. So don't look, don't look. Look away. Oh, wait, I might have a problem. Look away. Okay, great, you can look now. Oh, wait, no, I lied. All right. Is this linear? Now, what you're supposed to do is you're supposed to look at this and say, are all the solutions just vertical stretches of each other? Well, what do you think? These ones might be. They kind of look like it. Maybe they're not. Is there an asymptote? Is this exponential growth? We can't really tell. So these ones might be. But I can tell you for something sure, this purple one and this black one, these are not just constant multiples of each other, right? This is shooting off down to negative infinity over here, whereas it's behaving pretty nicely up here, the purple one. So yeah, even if these might be, and there's some ambiguity, and they're not, but there's some ambiguity, right? The top and the bottom ones certainly are not constant multiples of each other. This cannot be a linear differential equation because the solutions are not constant multiples of each other. And indeed, you may have seen this, but it's not a constant, or it's not a linear differential equation. It's y squared. T squared or x squared would be fine for linear. The dependent variable being squared, not linear anymore. Okay. So that's pretty much it for this video. If you're curious about what the linearity principle looks like for non-homogeneous differential equations, and how could you not be, we'll do that in the next video. To summarize what we talked about here, we basically just introduced this principle that said, if we have a linear homogeneous differential equation, find one solution, and you find them all by multiplying with by a constant multiple. Any constant multiple will work, and we have infinitely many solutions. The general solution, in fact. Anyway, that's all I have to say. Goodbye.